Chapter 14, Topics 14.5, Conservative Forces and Potential Energy, and Topic 14.6, Conservation of Energy. Conservative Forces, Potential Energy, and Conservation of Energy. Today's objective is to use the concept of conservative forces and determine the potential energy of such forces. Apply the principle of conservation of energy. So we'll come back to this presentation later. First, I'll explain the concepts through this notebook. So before so the particle, so the object can have two different types of potential energy. One is because of the spring effect, such as this balloon launcher or the mechanical spring. When the balloon launcher is being pulled back by this lady, the potential energy is stored into this launcher, and when she releases it, that potential energy results in like some velocity of the balloon at some angle. So this type of energy is called spring potential energy. Same applies to spring. If we stretch this spring and hold that spring at that position, we have actually stored energy in the spring. And when we release it, that energy is recovered. So we use letter V to define the potential energy. And because this energy is associated with elastic effect or spring effect, we call this PE, spring potential energy. And that can be calculated as 1/2 times K S square, where K is the spring constant and S is the deformation of the spring, how much length spring has changed when we stretch it. So if we stretch it this much, then this is called S. So it's 1/2 K S square for the spring potential energy. There is another type of potential energy. It's because of the height from the datum. It's because of the gravity. So we call this gravity potential energy. So for example, if we say that this surface here is our datum or reference plane, and relative to that the roller coaster is at some height h, then the roller coaster has stored potential energy in the form of gravitational potential energy. We call this Vg, and the formula for that is mgh, where m is mass of the coaster car, g is the gravitational acceleration, and h is the height from the datum. Spring potential energy is always positive because spring constant is positive, and deformation is square here, so that's positive. However, gravitational potential energy can be positive or it can be negative depending on where the datum is. So for example, if we define the datum at this surface A, then the potential energy will be 0 because the roller coaster car is at the datum. And relative to that point, potential energy of this coaster car will be negative. So if I say that this is my datum, then the coaster car is relative to datum, it's in the negative direction, and that's why the potential energy will be negative. So for this car here, and if the datum is here, potential energy is minus mgh. Once again, to summarize these concepts, let's look at this diagram here. So if the datum is this line, green line here, and if the particle is initially at position higher than datum, then the gravitational potential energy is positive, which is mgh. Mg is also called W, so you can write this as WH. And if it is below the datum, then it's negative potential energy, which is minus Wy, okay, or minus Wh, depending on what nomenclature we use. So these are two different types of potential energy. And the total potential energy V is combination of Ve plus Vg for the particle. Now, if the system contains spring, then we need to include Ve. If it does not contain spring, then yeah, we can only have these gravitational potential energy. But otherwise, if it has spring and gravity both, then the total potential energy is combination of Vg plus Ve. Conservative force. So conservative force is a force. So when the work done by force U, so we know that work done is equal to F ds cosine theta. So work done by force is independent of the path taken by the force, or independent of how the particle displaces from position 1 to position 2. Then that type of work done that type of force is called conservative force. For example, gravity is conservative force. So if we have particle, let's say if this is the datum, and this is the initial position 1 of the particle, and this is position 2 of the particle, then the gravitational potential energy depends only on the different height from the datum. It does not care how particle goes from 1 to 2, whether it can go in this line or it can go in straight line or it can do this zigzag and go to point 2. It doesn't care. So that type of work done by gravity is independent of the path, and that's why the gravitational force is conservative force. Same force, another type of force is spring force, that is conservative force, because when we stretch the spring, okay, whether it's horizontal stretch or vertical stretch, work done by spring is the same. It's independent of how we stretch the spring. It depends only on the initial and final length of the spring. So spring force is also conservative force. Friction, on the other hand, is non-conservative force, because if we have particle at position 1 here and we want that particle to go to position 2, then the friction acts in the opposite direction, and the work done by friction depends on the path, how particle goes from 1 to 2. If the particle goes through like zigzag path, then the friction force will be very different than it goes in straight line. So friction is non-conservative force. So now we are going to learn an important concept, conservation of energy. So conservation of energy states that when all the forces that are responsible for work done on a system of particles are conservative force, then the total energy remains constant between 2 points. So this total energy includes total potential energy plus total kinetic energy, which is 1/2 mv square, is constant. So in that case, we can say that if the particle goes from 1.1 to point 2, then the initial kinetic energy plus potential energy is equal to final kinetic energy plus potential energy. And this principle is called conservation of energy, that energy remains constant if the forces that all the forces that those do work are conservative forces. This concept does not apply to non-conservative forces. It only applies to conservative forces such as spring force or gravity. So when these are the only forces they do work, then the conservation of the energy concept is applied. We can actually apply that conservation of energy concept to this roller coaster here, such that if this is our datum, if this line is our reference line, and if this is our datum, then relative to that, at all the points, total energy T plus V remains constant. So TA plus VA is same as TB plus VB is same as TC plus VC. Okay, so total energy spring, like the kinetic energy plus potential energy at A is same as kinetic plus potential at B is same as kinetic energy plus potential energy at C. Okay? And using this concept, we can actually design the roller coaster or calculate the required datum height from the datum plane for coaster car at position A. Okay, so now we can go back and look at the presentation. The potential energy of a spring is always positive, because this is 1/2 k s square, where both k and s square are positive. When the potential energy of a conservative system increases, the kinetic energy, so see, T plus V is equal to constant. Okay, so if potential energy increases at different point, then kinetic energy has to go down. Okay, it's always decreases because it's the conservative system. So if one energy goes up, then the second energy goes down, kinetic and potential. And there are few application examples, such as the weight of the sacks resting on this platform causes the potential energy to be stored in the supporting spring. So when these weights are being kept on the platform, the springs, they get compressed and they store the potential energy. And when these weights are being lifted, then the spring potential energy is recovered. This is the example that the young woman pulls the water balloon launcher back, stretching each of the four elastic cords. If we know the unstretched length and stiffness of each cord, can we estimate the maximum height and the maximum range of the water balloon when it is released from the current position? Would we need to know any other information? Yes, we need to know the other information such as what is this angle, theta. If we know this angle information, then using projectile calculations, we can calculate how far and how high the balloon will go from the reference point. The roller coaster is released from rest at the top of the hill A. As the coaster moves down the hill, potential energy transferred into kinetic energy. So here, all it has is the potential energy. When it comes here, all it has is the kinetic energy. At this point, it is some potential plus kinetic. At this point also, it's some potential plus some kinetic. And finally, all kinetic energy. But the total energy, potential plus kinetic, is same throughout this ride. So what is the velocity of the coaster car when it is at B and at C? Also, how can we determine the minimum height of the hill A so that the car travels around both the inside loops without leaving the track? This is a very important question. And this is about conservative force that and the potential energy. That total potential energy is spring plus gravity. And when we have conservative forces, gravitational potential energy can be positive or negative. Spring potential energy is always positive, and conservation of energy T1 plus V1 is equal to T2 plus V2 is equal to constant, where T is kinetic energy and V is Vg plus Ve. If there is elastic element or spring present, otherwise it's only Vg. In the next video, we'll solve the problem based on this concept.